Hello friends, IBM is here with another episode of Learning Physics, and this is actually going to be the last unit of, the last part of kinematics. This is solved past paper questions in kinematics. This is AS Physics 9702, and this is going to be the last part of kinematics, and that is going to be part 4. So without wasting any time, remember in kinematics we are discussing questions involving a velocity, speed, acceleration, distance, displacement. We describe motion. We are using equations of motion. We have seen projectiles and a lot more. So without wasting time, let's go back to the past paper questions and we see part 4 of kinematics. Part 4 of kinematics. I think in part 3 we stopped on page 117, and I think in part 4 we should still pick up from 118. Part 4, a steel ball falls from a platform on a tower to the ground below as shown in the figure. So the vertical height is 192. The mass of the ball is 270 grams. Air resistance is negligible. Calculate the time taken for the ball to fall to the ground. So we want the time taken for the ball to fall to the ground. So using the equations of motion, S is equal to ut plus a half at squared. Since they gave us the vertical height, initial velocity is equal to 0. Initial velocity u is equal to 0. So it is going to fall through 192 meters. So this will be equal to a half times the acceleration is 9.81 times t squared. So I'll just press the calculator to find t. So t will be 192 times 2 divided by 9.81. So t is that one, get the square root of the answer, which is 6.256 or 6.3. So this is 6.3. Then the maximum kinetic energy of the ball. Calculate the maximum kinetic energy of the ball. If air resistance is negligible, then we shall say that the loss in gravitational potential energy should be equal to the gain in kinetic energy. So we have that the kinetic energy is equal to, it will now be equal to the loss in potential energy, which is mgh. So this will be 0.27, that is 270 grams times 9.81 times h, which is 192. I'm not equating kinetic energy to mgh. I'm just saying the loss in gravitational potential energy is the gain in kinetic energy. So the loss is mgh, which will be equal to the kinetic energy, 0.27 times 9.81 times 192. So that is 509. So this is going to be 509 joules. By the way, you could also use equations of motion to find the speed with which it hits the ground, such as v squared equals to u squared plus 2as. So v is going to be equal to the square root of u is 0. So this will be 2 times 9.81 times s, which is 192. So v will be 2 times 192 times 9.81. Then we find the square root. So that is the value of v. V is 61. V will be 61.4. Therefore, it means we can now find the maximum kinetic energy as a half times the mass, which is 0.27 times 61.4 squared. A half is 0.5 times 0.27 times 61.4 squared, which gives us 509 or approximately 510. State and explain the variation. State and explain the variation of the velocity of the ball with time as the ball falls to the ground. So as the ball falls to the ground, remember air resistance is negligible. So it means The velocity is directly proportional to the time, so it increases at a constant rate. So it increases at a constant rate as the acceleration is constant, or the resultant force is going to be constant. Since there is no acceleration, the velocity is proportional to time. Is proportional to time. So it increases. It increases at a constant rate. It increases at a constant rate because, or as acceleration is constant, that is due to gravity. Because the acceleration is constant, or the resultant force is a constant. That is only the weight. Show that the velocity of the ball on reaching the ground is approximately 60. I think that is the method we have already seen up there. V squared is equal to U squared plus 2AS. So V is going to be the square root of, it starts from rest, that is 0 squared plus 2 times 9.81, then times the distance is 192. So this is equal to 0, that is 2 times 9.81 times 192 square root, which gives us 61.37 or 38, 61.38, 61.38 or approximately 60 meters per second. Or you would use kinetic energy. You would use loss in kinetic energy is equal to, you would use kinetic energy is equal to a half mv squared, but the loss, the maximum kinetic energy we have got it from above. You would also say kinetic energy is equal to a half mv squared, which means that v is equal to the square root of 2 times the kinetic energy, which is 509 divided by the mass, which mass was, the mass was 0.27. So we have 2 times 509 divided by 0.27 square root. So that is, okay, that is 61.4, which is approximately 60 meters per second. 61.4 approximately 60 meters per second to one significant figure. Okay. In practice, air resistance is not negligible. The variation of the air resistance R with the velocity V of the ball is shown in the figure here. So we have air resistance with the velocity. In fact, we see that air resistance increases with velocity. Use the figure to state and explain qualitatively. So no need of quoting values. Qualitatively, the variation of the acceleration of the ball with the distance fallen by the ball. So if we think about the ball when falling downwards, it is falling due to the weight mg. But there is a resistive force in the opposite direction R, and R increases with the speed. So we are going to say that resistive force, resultant force, the resultant force is equal to the weight minus R, and R increases with velocity, and R increases with velocity. and R increases with velocity. The resistive force increases with velocity. And if R increases with velocity, it means the resultant force decreases. So the resultant force decreases. The resultant force decreases. Remember, resultant force is equal to mass times acceleration. So force is ma. If the resultant force decreases, it means the acceleration decreases. So hence acceleration decreases. Okay, the speed of the ball reaches 40 meters per second. Calculate its acceleration at this speed. The speed of the ball reaches 40 meters per second. So let's look at the graph. At 40 meters per second, what is the resistive force? So at 40 meters per second, the resistive force is 0.12345 0.6. So at 40 meters per second, R is 0.6 newtons. And we now want to find the acceleration. Remember, the resultant force F is equal to the weight, which is mg minus R. So it means ma is equal to mg minus R. So I can substitute. ma is um, the mass is 0.27. That is the mass of the ball. The acceleration is what I want to find. Should be equal to the mass, which is 0.27 times g, which is 9.81, then minus 0.6, that is minus 0.6 from the graph. Okay, so we have 0.27 times 9.81, then minus 0.6 divided by 0.27. So that gives us the acceleration as 7.6. That is 7.6. Use information from A and the figure 3.2 to state and explain whether the ball reaches terminal velocity. Let's check to see if the ball reaches terminal velocity. Note that at terminal velocity, the acceleration is going to be, or is supposed to be 0. So R should be equal to the weight at terminal velocity. At terminal velocity, the resultant force is 0. At terminal velocity, the weight is equal to R. mg is equal to R at terminal velocity. So we shall start with that. At terminal velocity, at terminal velocity, R should be equal to the weight. At terminal velocity, R should be equal to the weight because the resultant force is 0. R should be equal to the weight. In a bracket, it should be equal to 0.27 times 9.81, which is 0.27 times 9.81, which is 2.65. So at terminal velocity, R should be 2.65 at terminal velocity. R should be 2.65. But we notice that at 60 meters per second, because here they told us that show that the velocity of the ball on reaching the ground is approximately 60 meters per second. It reaches the ground at 60 meters per second. Let's check. At 60 meters per second, is R equals to the weight? So at terminal velocity, R should be equal to the weight, that is, it should be 2.65 newtons. But at 60 meters per second when it hits the ground. Let's see if it has already, the weight has already reached, R has already gone beyond 2.65. At 60 meters per second when it lands, R is less than the weight. Is that true? At 60 meters per second when it lands, R is less than the weight. Let's verify from the graph. At 60 meters per second, R is a value less than the weight. So it lands at 60 meters per second when R is not even yet terminal velocity. When R is not equal to the weight. So we have not, it doesn't reach terminal velocity. So, but at 60 meters per second when it lands, R is less than the weight. So it does not reach terminal velocity. Okay. Then the drag of force Fd acting on the sphere moving through a fluid is given by that expression. Determine the SI base units of K. K is a constant, rho is density, V is speed. So we make K the subject. So K making it the subject will be equal to Fd divided by rho times V squared. So Fd is force. Fd is going to be kilogram per meter squared, meters per second squared, that is force. Rho is density. Density is kilograms per meters cubed. And then V is speed, that is meters per second. So we now substitute the units. So K will have units as kilogram meters per second squared divided by kilogram meters per meter cubed times, because V is squared, this will be meters squared S power negative 2. So we can simplify this. So kilogram has cancelled out. In the numerator, you have meters per second squared divided by, of course, per second squared has also cancelled out. S power negative 2 has cancelled out. So you have meters over meters power negative 3 times meters power 2, which is going to be meters power negative 1. M over M power negative 1, that is M power 2. So this is M power 2. Ball of weight 1.5 newtons falls vertically from resting air. The drag force Fd acting on the ball is given by the expression in A. The ball reaches a constant terminal speed of 33 meters per second. Remember, at terminal speed, the weight equals to the drag if the earth thrust is negligible. For the instant when the ball is traveling at 25 meters per second, determine the drag force Fd on the ball. Okay, so we have that the drag force Fd is equal to K times density times V squared. But at terminal velocity, the drag force is going to be equal to the weight. The two forces are equal, so the resultant is 0. So this is going to be equal to 1.5. But this one is the same as K times density, then times 33 squared. That is at terminal velocity, which means that K times rho is going to be 1.5 divided by 33 squared. Then at 25 meters per second, at 25 meters per second, then the drag force Fd is equal to K times rho times 25 squared. So just substitute Fd, K times rho is 1.5 over 33, 1.5 divided by 33 squared, then times 25 squared. So that gives us 1.5 times 25 squared divided by 33 squared. So K is, FD is 0.86. The acceleration of the ball. We are going to determine the acceleration of the ball for 25 meters per second. So F resultant, the resultant force, remember it is given by mass times acceleration, which is going to be the weight minus Fd if there is a resultant force. Weight is greater than Fd. So this is going to give us, the weight, remember, was 1.5 minus the dragger force, which is 0.86. And also note that from F, because I want acceleration is going to be the resultant force divided by the mass. So acceleration is going to be the difference, which is 1.5 minus 0.86 divided by the mass. And the mass, sorry, I will put here m instead of acceleration, because that is obvious. I'll simply put here mass being equal to the weight over acceleration due to gravity. That is the mass. So because I want acceleration as the difference in this divided by the mass, I'm making A the subject. I'm dividing both sides by m, this side by m, the other side by m. So it means I will divide here by m, which is the weight. The weight is 1.5, divided by g, which is 9.81. 1.5 minus 0.86 divided by 1.5 divided by 9.81. So the answer there is 4.2. Describe the acceleration of the ball in B as its speed changes from 0 to 33. Acceleration. Remember, at 33 it is terminal velocity. So initially, when there is no air resistance, the initial acceleration is g. So initial acceleration is 9.81 meters per second squared. The acceleration then decreases as the speed increases because the air resistance or the resistance force increases. The acceleration then decreases as speed increases. The acceleration then decreases as speed increases, and of course at 33 meters per second the acceleration will be 0. The acceleration will be 0 because we shall have reached terminal velocity, so the acceleration will be 0. So it is initially 9.81, then it decreases as the speed increases, and to be 0 at 33 meters per second when we have reached terminal velocity. The variation with the time t of the velocity v of two cars P and Q is shown in the figure here. The cars travel in the same direction along a straight road. Car P passes car Q at t equals to 0. The speed limit for cars on the road is 100 kilometers per hour. State and explain whether car Q exceeds the speed limit. So if the speed limit is 100 kilometers per hour, let's check that in meters per second. 100 kilometers per hour is the same as 100 times 1000 to change it to meters, divide by 3600 to change it in meters per second. So that would be 100 times 1000 divided by 3600. That is 27.7, approximately 28 meters per second. Let's check the top speed of the car, of car Q. Car Q's top speed is 30 meters per second. The top speed is 30 meters per second, but the speed limit is 28 meters per second, but the car's top speed is 30 meters per second. That means because 28 meters per second is less than the car's top speed, it means the car has already exceeded the speed limit. So the car exceeds the speed limit. So this is less than the car's top speed. It is less than the car's top speed. So the car exceeds the speed limit. Because it stops, the speed limit is less than the car's top speed. So the car exceeds the speed limit. Actually, the acceleration of car P, of course, acceleration is change in velocity over time, which is equivalent to the gradient for car P. For car P, we shall check in the horizontal axis, I'll just use 12 minus 0. Then on the vertical axis, this is, I think this is 24 minus 20. So that is 24 minus 20 divided by 12 minus 0. So 24 minus 20 divided by 12, that is 1 over 3, that is 0.33. Determine the distance between the two cars at time t equals to 12. At time t equals to 12, we want the distance between the two cars. So let's first find the distance of car Q, which is area under the graph of Q, and distance of car P, which is area under the graph of car of P. Then we find the difference because we want the distance between them. So distance is equal to the area under the graph. So distance traveled by P is going to be a half. I'll just take it as a trapezium for P. I'll take it as a trapezium for P. It is the area under this part of the graph. So A will be 20, B will be 24, and the height will be 12. So I'll simply say a half into, I'm using the formula of a trapezium, so that is 20, A plus B times height, which is 12. So that one is 20 plus 24 divided by 2 times 12. So that is 264 meters. Then distance by Q will be a half. It is a triangle. A half times the base could be 12, and the height is 30, which is equal to 0.5 times 12 times 30, which is 180 meters. So we want the distance between the two cars. So distance between Distance between the cars is going to be equal to 264 minus 180. 264 minus 180, that is 84. From time t equals 12 seconds, the velocity of the car remains constant at its value at 12 seconds. Determine the time t at which car Q passes car P. What the time at which car Q passes car P. So since we have the extra distance, we can just find the difference in the speed. To find the extra time, we see the distance between them. Let's find the extra difference in speed. So difference in speed, the difference in speed, because the velocity of each car remains constant. So let's see the difference in speed. Difference in speed is equal to 30 minus 24, which is equal to 6 meters per second. Difference in the top speed at 12 seconds. Then it means the extra time, the time t at which the car Q passes car P. So the extra time between the cars, extra time is going to be equal to the difference in the distance between the two cars and the speed, the difference in the speed. The extra time is actually 14. I think 84 over 6. I think that is 14 seconds. That is the extra time. So we want the time at which car Q passes car P. At 12 seconds, we have seen that the extra time required for the car Q to pass car P is 14 seconds. That means the time at which it passes, it is going to be the 12 seconds plus the 14 seconds. So the time t, so t is going to be equal to 12 plus 14, which gives us 26 seconds. After 26 seconds, car Q will pass car P. Alternatively, we can use simple relations. We can use at the time when one car passes the other one, it means that the total distance covered is going to be actually the same. That means 180 plus, that is for car Q, it's 180 plus 30 times t, that is if it remains with a speed of 30 times the time t when they actually meet, should be equal to the distance which the other one has also covered, which will be 264 plus the time its speed is 24, then times t. The t is the time when they meet, or when one passes the other. So that means we can now solve for t. So collecting like terms, the other side we have 30 t minus 24 t. The other side we have 264 minus 180. So this is 6t is equal to 264 minus 180, that is 84. 264 minus 180, I think that is 84. Is it 84? Yes. So it means the time required for them to pass each other is going to be 84 over 6, which is going to be 14. So that will be the time when the extra time they pass after 12 seconds. So the answer we want still will be t plus, will be 12 plus that 14 seconds. So this is the time needed for the extra time needed for Q to pass Q, for Q to pass P. Define displacement. So displacement is actually distance in a specified direction. Distance in a specified in a specified direction from a point. Distance in a specified direction from a point. Then acceleration, that one is the rate of change. Rate of change of velocity. A remote controlled toy car moves up a ramp and travels across a gap to land on another ramp. The car leaves ramp P with a velocity of 55. So it means this angle here is still going to be the angle is still going to be theta. The horizontal component of the car's velocity as it leaves the ramp is 4.6. So resolving that horizontally, it is 5.5 cos theta in the horizontal. In the vertical, it is going to be 5.5 sine theta. The car lands at, so it means 5.5 cos theta is 4.6 because that's the horizontal component. The car lands at the top of ramp Q. The tops of both ramps are the same height and are distance d apart. Air resistance is negligible. Show that the car leaves ramp P with a vertical component v of velocity of 3.0 meters per second. So we have seen that the horizontal component 5.5 cos theta is equal to 4.6. So the vertical component, which is going to be 5.5 sine, or the vertical component, which is 5.5 sine theta, is going to be equal to, I'll call it V in the vertical. So we can, since we have, we can still find, or we can easily find theta from the first part here. This one means that theta is going to be the cos inverse of 4.6 divided by 5.5, which is, so cos inverse of 4.6 divided by 5.5. Theta is 33.2 degrees. So it means the vertical component V in the Y is going to be 5.5 sine of 33.2, which is 5.5 sine of 33.2. That is 3.0. So V in the vertical is 3.0 meters per second. Oh, by the way, we can alternatively find this. If the horizontal component has been given, this is another method, as 4.6. We have the resultant velocity was 5.5 at an angle theta, and we want the vertical component, which is V in the vertical. It is going to be pointing upwards. So we can use Pythagoras theorem. So it means 5.5 squared is equal to 4.6 squared plus V in the Y squared. That means V in the Y is going to be equal to the square root of 5.5 squared minus 4.6 squared, which is 5.5 squared minus 4.6 squared under square root, and that is 3.0. So you could use that method. Okay. Determine the time taken for the car to travel between the ramps. Time taken between the ramps. So since we have the horizontal distance, the horizontal component, or we can even use if because it is coming, it is leaving point, this vertical height is the same. So it means the vertical displacement, if I consider vertical motion, vertical displacement is 0. It starts from this level, it comes back to the same horizontal level. So vertical displacement is 0. So using S is equal to UT plus a half 30 squared. Vertical displacement is 0. So 0 is equal to initial velocity in the vertical. I'm considering vertical motion. This is acceleration in the vertical. Vertical is 3.0. Vertical component 3.0 times t minus, because it's moving against gravity, 9.81 times t squared. So it means t is going to be equal to 3.0 times 2t, but 1t has cancelled because of the 0 on the other side, divide by 9.81. 1t has cancelled because there is 0 this side. I take 3t on the other side and t cancels. 1t cancels. So this will be 6 divided by 9.81, which is 0.61. 0.61. Alternatively, we can use V equals to U plus AT. You can use maximum height and multiply that time by 2. Or you know that final velocity at the other ramp is going to be negative 3.0 in the vertical, but initial velocity was 3.0 going upwards. Then this will be minus, acceleration is 9.81, then times t. So it starts with this velocity of 3.0 upwards. We expect it to arrive at the same level with the same velocity but in the opposite direction. That's why you say minus here. So that means we have that negative 6.0 is equal to negative 9.81 times t, which still gives us t as 0.61 seconds. So you can also use that method. Calculate the horizontal distance d. So we shall consider horizontal motion. Displacement in the horizontal is initial velocity in the horizontal times t plus a half. Acceleration in the horizontal times t squared. Remember, acceleration in the horizontal is 0 because there is no force in the horizontal. So the displacement in the horizontal is d. Initial velocity in the horizontal was 4.6. Then times the time. Of course, time is the same either in the horizontal or vertical. So this is times 0.61. The other part is 0. So we shall just have that times 4.6, which is 2.8. So d is 2.8. Calculate the ratio kinetic energy of the car at its maximum height over kinetic energy of the car as it leaves ramp P. So at maximum height, remember V in the vertical is 0. It is only V in the horizontal which counts. So V at maximum height is only V in the horizontal, which is 4.6 meters per second. V in the vertical is equal to 0. So it means we know that kinetic energy is a half m v squared. So let's find the ratio. The ratio will therefore be equal to a half times the mass times v. At maximum height is only v in the horizontal, which is 4.6 squared, divided by a half times the mass times v as it leaves the ramp is 5.5. So that's 5.5 squared. So this half cancels. 4.6 squared divided by 5.5 squared. So that gives us 0.6995 or 0.70. Ramp Q is removed. The car again leaves ramp P as in B and now lands directly on the ground. It means its speed now it lands with a higher speed because it continues falling below the point of projection. The car leaves ramp P at equals to 0. It will start with a certain velocity. Let's say vertical component is Vy. So V in the Y will be a certain value, which we have already seen earlier on. But they said numerical values are not needed, so I will not include any value there. Then after a certain time, it lands on the ground at time t equals to capital T. Since it is now falling to a larger distance, it will take a shorter time to reach the maximum height, but it will take more time to reach to hit the ground. So the time from 0 to when it reaches maximum height, that time is going to be smaller than when it lands. So I'll consider this time to reach maximum height. I will consider it here. Let it be somewhere here, and then it lands. So that is a straight line. From V, initial velocity, initial value of V in the vertical is a certain value, not 0. But then the velocity decreases as it goes to the highest point. And after then, the velocity increases in the opposite direction. So the line continues downwards until it reaches the ground at a higher value of V. So the graph will be a straight line. It will touch at t on a higher value of V than it started at t equals to 0. So I will not need to put that there. So it will be a straight line from a positive value of V at t equals to 0 to a negative value of V in the vertical. But this straight line ends at t equals to capital T, and the final magnitude of the vertical component is greater than the initial value at t equals to 0. That's why you see that when you compare this value here with the other one, this one is greater because it continues below. This was the point of projection. It went upwards, then it continued below because the other ramp was removed. So it continued below until it hit the ground. So it will hit the ground with a higher value of speed than the one it had when it was leaving the ramp. Okay. A golfer strikes a ball so that it leaves horizontal ground with a velocity of 6.0 meters per second at an angle theta to the horizontal as illustrated here. The magnitude of the initial vertical component Vy of the velocity is 4.8 meters per second. That is the vertical component. Assume that air resistance is negligible. Show that the magnitude of the initial horizontal component Vx is 3.6. Okay. So first of all, we notice that we can even use Pythagoras theorem, but first of all, we notice when we resolve 6 to the horizontal, Vx is going to be equal to 6 cos theta then Vy is equal to 6 Vy is 6 sine. What's wrong with my pen? So Vy is 6 sine theta, Vx is 6 cos theta. So we are saying that 6 sine theta is equal to 4.8 and 6 cos theta is equal to Vx. So we want to show Vx is 3.6. So from this one, you notice that theta will be the sine inverse of 4.8 divided by 6, which is 4.8 divided by 6. So theta is sine inverse of 4.8 divided by 6, which is 53.1. 53.1 degrees. So it means Vx is going to be 6 cos 53.1. 6 cos 53.1, that is 3.6. Alternatively, I said we can use Pythagoras theorem. The vertical is 4.8 and this one is 6. So we want the horizontal. So using Pythagoras theorem, this is hypotenuse, this is 4.8 is adjacent because the angle is here. So we want the opposite. So this is going to be 6. Vx is going to be the square root of 6 squared minus 4.8 squared, which will be 6 squared minus 4.8 squared, then square root of the answer, which is 3.6. Exactly, 3.6 meters per second. The ball leaves the ground at time t equals to 0 and reaches its maximum height at 0.49 seconds. Maximum height is 0.49 seconds. On the figure, sketch separate lines to show the variation with the time t until the ball returns to the ground of the vertical component Vy. Label this line y. It reaches maximum height at 0.49. Remember, at maximum height, velocity becomes 0. So we look for 0.49 where velocity will be 0 on the vertical. So on the x-axis, it is 0.1 divided by 5. The scale is 0.1 divided by 5 small squares. Each small square is 0.02. So this is 0.424648. 49 is here. 49 is there. 0.49 is in between there in the box. So there the graph should cross the x-axis. Okay. We have the initial velocity in the vertical. The initial velocity in the vertical was 4.8. So our graph starts from 4.8 on the vertical. Each small square is 1 over 5, which is 0.2. 1, 2, 3, 4. So 4.8 is there. Then we have also seen that we can find the time. We may find the time. What time do they want? Sketch separate lines show the variation with time t until the ball returns to the ground. Of course, if it takes 0.49 to go upwards, we expect it to take another 0.49 to return. So 0.49 times 2. 0.49 times 2, that is 0.98. We look for 0.98. The ball will be on the ground and it will return with the same speed in the vertical. If it comes to the same level, it will return to the same speed of 4.8. So I look for 4.8 again, but the time is 0.49. Where is 0.49? This is 0.929496. I need 0.98 against negative. This time it will be negative 4.8 because it will be in the opposite direction. So negative 4.8, I think it is this point. 0.98 against negative 4.8. So that is a straight line which goes through that point, the origin up to, let me try to increase the weight slightly. Okay. I think 4.9 is here, not the previous position. Okay, so the graph touches this point to process through the center there, then 4.8, as simple as that. Then, so they said label this y. So I'll label this line y. Then for the horizontal component, for it remains constant and it was 3.6. So I just look for 3.6, 3.2, 4, 6. 6 is there. So it remains constant up to 0.98. For the horizontal component will remain constant up to 0.98 seconds. The horizontal component of velocity does not change because the acceleration is 0. There is no force in the horizontal. So that is supposed to be the line. So we must have a straight line which goes through 0 and 4.8. 0, initially it starts from 0 and 4.8. At t equals to 0, the velocity was 4.8. Then at 0.49, the velocity becomes 0. And at 0.98, the velocity goes to negative 4.8. That's when it hits the ground. Then also we have that the velocity for a horizontal component, the velocity remains 3.6 throughout. It remains constant. That is line x. Okay. Calculate the maximum height reached by the ball. Maximum height reached by the ball. So I can use several methods because for maximum height there are so many methods to use. If I consider v squared equals to u squared plus 2as, I'm considering vertical motion. At maximum height, v is 0, so I will say 0 squared is equal to initial velocity in the vertical is 4.8 squared minus 2 times 9.81, then times the height h. So h is equal to, I'll just press my calculator. So I have 4.8 squared on one side divided by 2 times 9.81. So h is 1.2 meters. That is method number 1. Method number 2, I would use another equation. Maybe I can use S is equal to a half into U plus V times T to find the maximum the maximum height. So this will be a half. Initial velocity was in the vertical is 4.8 plus at maximum height it is 0. But the time to reach maximum height was given as 0.49. So I have 0.5 times 4.8 times 0.49, which gives me h or distance s as 1.2 meters. I could also use s. This is method number 3. I could use s equals to ut plus a half at squared. They have mentioned the time to reach maximum height as 0.4, so s is going to be equal to initial velocity in the vertical is 4.8, time is 0.49 minus, because it moves against gravity, a half times 9.81 times 0.49 squared. So I have 4.8 times 0.49 minus 0.5 times 9.81 times 0.49 squared, which is still giving me s as 1.2. So the maximum height is 1.2 using either methods. For the movement of the ball from the ground to its maximum height, determine the ratio. Kinetic energy at maximum height. We have seen a similar question, and we know that at maximum height, the velocity is only the one in the horizontal over change in gravitational potential energy. So V at maximum height is only V in the horizontal. We have said that V in the vertical becomes what? 0. We know that kinetic energy is a half mv squared, and the change in potential energy is equal to mg times the change in the height h. So let's find the ratio. The ratio will be equal to kinetic energy, which will be a half m. V at maximum height is going to be the velocity in the horizontal, which was 3.6. So that will be times 3.6 squared divided by m times g, which is 9.81, times the change in the value of h. The maximum height is 1.2, so that's times 1.2. So that will be m has cancelled out. So we have 0.5 times 3.6 squared divided by 9.81 times 1.2. So that is 0.55. So this is 0.55. That's the ratio. In practice, significant air resistance acts on the ball. Explain why the actual time for the ball to reach maximum height is less than the time calculated when air resistance is assumed negligible. So when the ball is going upwards, let's say this arrow shows the direction of motion. The weight is downwards, but air resistance will be also downwards. So if air resistance is not negligible, it means the resultant force is greater, so the deceleration is greater. Because motion is in the opposite direction to the resultant force, it is a deceleration. So it means the deceleration is greater. So that means the time is going to be less. So we can say resultant force is equal to the weight plus the force due to air resistance. Resultant force is equal to the weight plus the force due to air resistance. Because the two are downwards, it means the resultant force is greater. So note that the resultant force is greater but in the opposite direction to the motion. So the acceleration is a deceleration. So the deceleration is greater because resultant force is equal to ma. So since F is greater, A is greater, but this is in the opposite direction to motion. So it is a deceleration. So we say that the deceleration is greater. So deceleration is greater, hence less time. Hence less time to reach maximum height. Because the resultant force downwards is greater, it will take less time to reach the maximum height because of a greater deceleration. A small block is lifted vertically upwards by a toy aircraft as illustrated in the figure. As the block is moving upwards, the string breaks at t equals to 0. The block initially continues moving upwards, we can see that from the graph, and then hits the ground at time t equals 0.9 seconds. The variation with the time t of the velocity v of the block is shown here. Air resistance is negligible, that is very important, so equations of motion can work. State the feature of the graph that shows that the block has a constant acceleration. I think it is a straight line, so it means it has a constant gradient. Constant acceleration, straight line shows a constant gradient. Straight line, thus constant gradient. constant gradient. Remember, the gradient is the acceleration. Use the figure to determine the height of the block above the ground. Height. It reaches, it continues moving upwards to the highest point and then falls back to the ground. So this part here is the area under the ground, the distance, because after 0.2 seconds, it is now returning and reaches the ground at 0.9. So this area here is the area which represents the distance from the maximum point to the ground. So they want us to determine the height of the block above the ground when the string breaks. Before it breaks, the block was as soon as it breaks, the block would travel this distance here. So it means we can get the distance it travels when the string breaks minus the distance it falls downwards when it had reached maximum height, to find the distance or the height of the block above the ground when the string just breaks. Okay, so the displacement is going to be equal to first of all, let's find the displacement until 0.2 seconds. When it is going, it continues upwards after the string has broken. So we have displacement until 0.2 seconds. It continues upwards for 0.2 seconds, which is going to be equal to the area under the line, and that is a triangle half times the base, which is 0.2, and the vertical height is 1.96. So that is the distance it travels when the string breaks, which I think is 0.196. 0.196 in meters. Then we can find displacement after 0.2 seconds, that when it is returning to the ground. So displacement after 0.20 seconds. This is also an area under that line, which is a triangle half, times the base. The base is going to be 0.9 minus 0.2, which is 0.7, and the height is 6.87. 86. So that is 0.5 times 0.7 times 6.86, which is 2.401. 2.401 meters. Yes, 2.401 meters. So we now want the height. Note that from 0.2 the body is falling. It first continues upwards, then it falls. It first continues upwards to the maximum height for 0.2 seconds, then it falls back until it reaches the ground. So if it started from here, 0.2 it reaches maximum height, then it now falls in the opposite direction. It falls below the point of projection. So we want this height here. This is the distance before, this is the distance after 0.2. So we want that height before at the height when the string breaks. So the height is going to be equal to 2.401 minus 0.196. 2.401 minus 0.196. So that is 2.2. That is automatically 2.2. By the way, you can use equations of motion, but that will be a long process. You can use S is equal to ut plus a half at squared and v squared equals to u squared plus 2as. You get S using the first part, you get S using the second part, and of course you subtract. Maybe I can try it here. So first of all, I'll use v squared equals to u squared plus 2as. So v squared equals to u squared plus 2as. Now this is going to be s1 when it goes to the highest point. So at the highest point, v0 squared equals to initial velocity, which was 1.96 squared minus 2 times 9.81 times s1. So s1 is, I'm just going to press the calculator, 1.96 squared divided by 2 times 9.81, and that gives us 0.196 meters. Then we can get we can get S2 using the same formula maybe. Again, v squared, it reaches maximum velocity at 6.86 when it returns. So I'll say 6.86 squared is equal to initial velocity. We are considering it starting from the highest point. So it starts from 0 at the highest point. So that will be 0 squared. Since it is falling, I will not subtract, I will just say plus. I consider it when it is just leaving the highest point. Just leaving the highest point here where u will be 0 when it is falling downwards from the graph. At that point, v is 0. So this will be equal to, this will be 2 times 9.81 again times s2. I'll find s2 as 6.86 squared divided by 2 times 9.81. So that is giving me 2.399. Then we now find the difference. So the height h is going to be that difference. So 2.399 minus 0.196, which is approximately 2.2. So that can work. Okay, the block has a weight of 0.86 newtons. Calculate the difference in gravitational potential energy of the block between t equals to 0 t equals to 0.90 seconds. Difference in gravitational potential energy. So we know that the difference in potential energy is equal to mg times difference in height h. So since the mg is the weight, so this will be 0.86. The difference in height is simply going to be the height that we have calculated above. So that is going to be 2.2. So this will be 0.86 times 2.2, which is 1.889 or 1.9. On the figure, sketch a line to show variation of distance moved by the block with the time t from t equals to 0 to t equals 0.6. Numerical values of distance are not required. So we notice that the speed is decreasing. How do we show that the speed is decreasing? Is by making the graph of distance to have a decreasing gradient. And the speed becomes 0 at 0.2 seconds. So the speed starts with a certain value. So our graph should have a gradient initially, but then the gradient should be decreasing because the speed decreases. At 0.2, the speed is also, the line should be horizontal so that the gradient is 0 at 0.2 seconds. Therefore, that is very easy to sketch. So we shall start with some gradient, which therefore starts decreasing because there's a speed. So we start with a gradient which starts decreasing, and it becomes horizontal at 0.2 because at 0.2 the gradient must be 0 since the speed reaches 0. So our graph will look like that. You can draw a perfect smooth curve with a pencil. So the gradient decreases and is 0. It must be 0 at 0.2. It must be a horizontal line at 0.2 only. A block of greater mass is now released from the same height. Now mass is coming into play. Air resistance is still negligible. State and explain the effect, if any, of the increased mass on the speed with which the block hits the ground. If air resistance is negligible, the acceleration of free fall does not change. It is not dependent on the mass, so there is no effect. So acceleration of free fall does not change since it is not dependent on mass. Since it is not dependent on mass, and so no effect. Because the acceleration is not dependent on mass, it does not change even if we change the mass. Therefore, there will be no effect, because when you look at the formula, you see that v squared is equal to u squared plus 2as. Mass does not come into play even if we change the mass. The acceleration of free fall remains the same. Complete the table by putting a tick in the appropriate column to indicate whether the listed quantities are scalar or vectors. So we now know that there are 6 vectors. Acceleration is one of them, momentum is one of them. The rest are scalars, density, and temperature. The 6 vectors are acceleration, displacement, velocity. We have momentum or impulse. We have force or weight. And we have moment or torque. Everything else at this level will be a scalar quantity. A toy train moves along a straight section of track as shown here. The variation with time t of distance d moved by the train is shown. Describe qualitatively, no need of quoting values, the motion of the train between t equals to 0 to t equals to 1. Do we see that the gradient decreases? So the speed decreases. It is decelerating. So the train decelerates between t equals to 0 to t equals to 1 as the speed or velocity decreases. So the train decelerates between t equals to 0 seconds to t equals to 1.0 seconds as the velocity decreases. How do we see that the velocity is decreasing? The graph is becoming horizontal, meaning that the gradient is decreasing. A decreasing gradient of displacement against time means a decreasing velocity. Determine the speed of the train at t equals to 2 seconds. Of course, this is a straight line. We can just find the gradient. I'll use full values. The gradient is constant, so even if I use full values, so I'll use this one, and I think this is 0.56 because the scale is 0.1 divided by 5, which is 0.02. That is 0.56, and I'll use which other point should I use? Let me use 1.5. 1, 2, 3, 4, 5. Okay, let me use 5. This is 1.5. The velocity, the displacement there is 0.2. So I'm taking the gradient, find the speed. So the speed is equal to the gradient. Which is going to be equal to 0.56 minus 0.20 divided by 3.0 minus 1.5. So 0.56 minus 0.2 divided by 1.5. So that is 0.24. The straight section of track in B is part of the loop of track shown here. The train completes exactly one lap of the loop. State and explain the average velocity of the train over the one complete lap. Of course, here the answer is 0. Because it's one lap, the change in displacement is 0. The shortest distance between the starting point and the final point is 0. And velocity is the rate of change of displacement. Since the change in displacement is 0, since we are coming back to the same point, then it means the velocity is going to be 0. So we simply say displacement is 0. Displacement is 0, so the average velocity is 0. The ball is fired horizontally with a speed of 41 meters per second from a stationary cannon at the top of a hill. The ball lands on a horizontal ground and is a vertical distance 57 meters below the cannon as shown in the figure. Assume air resistance is negligible. Show that the time taken for the ball to reach the ground after being fired is 3.4 seconds. So since they have given us the vertical distance, we shall use vertical motion. Considering vertical motion, I will consider the displacement in the vertical, the initial velocity in the vertical times time plus a half, acceleration in the vertical times t squared. Remember, if it is fired horizontally, initial velocity in the vertical is 0. So the vertical displacement is 57 equals to 0 plus a half times in the vertical acceleration is 9.81 then times t squared. So I will just say 57 times 2 divided by 9.81. Then I find the square root of the answer. So it means t is equal to 3.4 seconds. If you want to show the working, you can say, okay, which implies t is equal to the square root of 2 times 57 divided by 9.81, which is 3.4. Calculate the horizontal distance of the ball from the cannon at the point where the ball lands on the ground. Horizontal. So we are going to consider horizontal motion. S in the horizontal, initial velocity in the horizontal times time, plus a half acceleration in the horizontal times t squared. Remember, acceleration in the horizontal is 0 because there is no force in the horizontal. So S in the horizontal is equal to initial velocity in the horizontal. The velocity in the horizontal remains constant, so that will be 41. The time is the same because time is a scalar, so that's 3.4. So I just say 41 times 3.4, which gives us 139.4, approximately 140. Determine the magnitude of the displacement of the ball from the cannon at the point where the ball lands on the ground. We now want displacement. We have velocity, we have displacement in the horizontal, we have displacement in the vertical. We have speed distance in the horizontal as 140. We have distance in the vertical, it was 57. S in the horizontal is 140 meters. S in the vertical is 57 meters. The resultant value of S is going to be the square root of 140 squared plus 57 squared because they are at right angles. So 140 squared plus 57 squared equals that. Square root of the answer is 151. So this is 151 meters or approximately 150. 150 meters. How am I writing 150? The ball leaves the cannon at time t equals to 0. Sketch a graph to show the variation of the magnitude of v of the vertical component. Of course, the vertical component increases if it is falling downwards. Vertical component of the velocity of the ball when with the time at t equals to 0. Initially, there is no velocity in the vertical, so our graph starts from the origin. Since air resistance is negligible, the acceleration is constant. So this is going to be a straight line. So that the gradient is constant. So that will be a straight line up to 3.4. A straight line gives us a constant acceleration if air resistance is negligible. Since acceleration is constant, it is going to be a straight line so that the gradient is constant because air resistance is negligible. This graph starts from 0, 0 because initially in the vertical there was no velocity since the initial velocity was in the horizontal. But the velocity in the vertical increases because there is an acceleration as the ball moves. The cannon recoils horizontally with a speed of 0.34 when it fires the ball. The total mass of the ball and the cannon is 1480 kilograms. Assume that no external horizontal forces act on the ball cannon system. Determine to 3 significant figures the mass of the ball. So here we are going to use momentum and we are going to conserve momentum. So momentum is mass times velocity. So total momentum before, of course, initially the system was at rest. That means total initial momentum was 0. So total momentum before is 0, but after the mass, let the mass of the ball be m. I'm going to say the mass of the ball is m. So the mass of the ball is m times its velocity, which is 41 after it is being fired, plus the momentum of the cannon, which is going to be, because it recoils, they said it recoils, that means it moves in the opposite direction. So this will plus a negative. I'll put a negative to show opposite direction. If the mass of the ball is m, then the mass of the cannon is going to be 1480 minus m. This is the mass of the cannon. If the mass of the ball is m, then the mass of the cannon is 1840 minus m because their total mass is 1840. So this will be 1480 minus m times the velocity, which is they say the speed of the cannon when it requires 0.34. So that is times 0.34. So that is total momentum after. Now we just simplify. We take the other on the other side. So we have that 41m equals 2. On the left hand, the right hand side, we have 1480 minus m, then times 0.34. So this is times 0.340. Open the bracket and collect like terms. So when I open the bracket, on the left hand side, I'm going to have 41 plus 0.34. And that is 41.34 m. On the right hand side, I'm going to have 1480 times 0.34. I'm opening that bracket by multiplying everything by 0.34. So this is side I have 503.2. Now I divide both sides. So divide by 41.34. That is 12.17 or 12.2. So the mass is 12.17 or approximately 12.2 because they said to 3 significant figures. So this is 12.2. For those who are good at mathematics, we can use mathematical relations. So the total since the initial momentum is 0, then we can say the momentum of the coil of the cannon, I'll call it mc, times its speed is 0.34, should be equal to the momentum of the ball after. That will be mass of the ball times its speed, which is 41. Because total momentum initially was 0, so it means the total momentum of the cannon is now going to be equal to total momentum of the ball because they move in opposite direction. So that is fine. But the total mass of the cannon plus the mass of the ball is 1480. Now we solve the two equations. From the first equation here, you notice that the mass of the cannon is going to be 41 over 0.34 times the mass of the ball. I'm just using substitution. So I'm now substituting 41 over 0.34 times the mass of the ball plus the mass of the ball is going to be 1480. So common factor is mass of the ball. So this means mass of the ball is equal to 1480 divided by, in brackets I have 41 over 0.34 plus 1, because mass of the ball was a common factor here. So I have to move the one here is because I was making mass of the ball the subject. So now solve this. 1480 divided by, open brackets. We have 41 divided by 0.34 plus 1. So that is 12.2. So that is 12.2 kilograms. Okay, I hope that is fine. The cannon now fires a ball of smaller mass. Assume that air resistance is still negligible. State and explain the change, if any, to the graph in the figure due to the decreased mass of the ball. So we want to see what happens to that figure. But of course, note that that figure is for velocity against time, and the velocity against time is not depending on the mass. It is actually depending on the acceleration, which is not changed because of change in mass. Therefore, we simply say there is no change. There is no change to the graph. Reason? Because the acceleration of free fall is not changed. Why is the acceleration of free fall not changed? It does not depend on, since it does not depend, is not dependent on mass. Since it is not dependent on mass. Since it is not dependent on mass. A child of weight 330 newtons is at point X at the top of a slide. The slide is at the edge of a swimming pool as shown in the figure. So we can look at the figure. The child moves from rest to the lowest point of the slide, that is a vertical distance 4 meters below X. The child continues moving towards Y, which is at the end of the slide, and the vertical distance 0.11. 1.1 meter above the lowest point. The kinetic energy of the child is 540 at y. Calculate the difference in the gravitational potential energy of the child between at points x and y. So we want difference in gravitational potential energy. So difference in gravitational potential energy is going to be equal to mg times difference in the value of the height h. So let's see the mass. Do we have the mass? They gave us the weight. So mg is the weight, which is 330 times the change in height, which is 4.0 minus 1.1. 4.0 minus 1.1. So 330 times 4 minus 1.1. That is 957. Sorry, why do I write 647? 957, which is approximately 960. An average friction force of 52 newtons acts on the child when moving from x to y. By considering changes in energy, determine the distance moved by the child from x to y. So you see that the decrease in gravitational potential energy is not the same as the kinetic energy at y. That means some energy must have been wasted in overcoming friction. So work done is going to be equal to 960 minus 540. That is to overcome the resistive forces or the average friction force. And we know that the work done is equal to the force times the distance. So the distance is going to be the work done over the frictional force. So that is 960 minus 540 divided by the frictional force, which is 52 newtons. 960 minus 540 divided by 52. So that is 8.1. The child leaves the slide at point Y with a velocity that is at an angle of 41 degrees to the horizontal. The path of the child through the air is shown. Point Z is the highest point. If Z is the highest point, we know that at maximum height V is 0. Assume that air resistance is still negligible. Calculate the speed of the child at Y. Where is Y? Is just at Y. They gave us the kinetic energy, so that means I'll simply say kinetic energy is equal to a half m v squared, but they gave us the kinetic energy as 540 at Y. And we also know that the mass is going to be equal to the weight divided by g, because weight is mg. So the mass is going to be 330 divided by 9.81. So let's find v. Or let's just substitute here. So we have a half times 330 over 9.81, and this is times v squared is equal to 540. So I'll check my calculator. 330 divided by, open brackets, 2 times 9.81. Then on the left hand side, I'll say 540 divided by that answer, and I find the square root of the answer, which is 5.6666. So V is 5.67 or 5.7. So the speed is 5.7. Then point Z. Remember, point Z is the highest point, where speed there is going to only be equal to the horizontal component of the velocity. So the speed there is equal to the horizontal component of velocity. horizontal component of velocity, the vertical component is 0. Since, I'll put here for explanation, since vertical component is 0. So this is going to be the horizontal. Remember, the horizontal component does not change. There is no acceleration in the horizontal. So I look for the horizontal component. I will resolve this in the horizontal. I'll resolve the speed at y we have got as 5.7. Resolving it in the horizontal to be 5.7 cos of 41. So that will be 5.7 cos of 41. 5.7 cos 41, which is 4.3. Okay, define velocity. Of course, velocity is the rate of change of velocity. Rate of change of displacement. Rate of change of displacement. Rate of change of displacement. A remote controlled toy aircraft is flying horizontally in a wind. The figure shows vectors. It is actually, these vectors are to scale. I don't know whether the scale was maintained here. It shows vectors to scale of the wind and of the aircraft in still air. The velocity of the aircraft in still air is 42 meters per second to the north. The velocity of the wind is 23 meters per second, 54 degrees east of south. Determine the magnitude of the resultant velocity of the aircraft. So since they did not tell us which method to use, we can first use, I will just complete this to scale by joining head to tail. So I'll just transfer the velocity of the wind downwards and I represent it with its length. So taking this downwards, that is 2 point. The length of the line representing velocity of the wind is 2 point. Mine is 2.12. Mine is 2.2. So I'll extend this downwards, joining the vectors head to tail. I may not be very accurate because I'm drawing on a computer. So I'll measure off 2.2 on this line. Around there. I'll draw the resultant vector. The resultant will be here. So this is going to be the resultant. And this is the velocity of the wind, which is 223. So this is the wind. Now the vectors have been joined head to tail. I can, using a scale, I will measure. First of all, let me see the scale. Four point 1, 2, 4.2, 4.3. So 4.3 centimeters is representing 42 meters. It is representing 42 meters per second. You can check you just measure on your book. You measure on your book. So for me, for my computer, 4.3 centimeters is representing 42 meters per second. That means the scale is going to be 1 centimeter representing 42 over 4.3 meters per second. So I'm measuring the length, which I've labeled R, to multiply it by the scale to get the resultant. So that is 3.123. So r is equal to 3.3 times the scale, which is 42 over 4.3. So you can also check yours. Here I'm using scale. This is method 1, using a scale. You choose the scale, you find the scale by taking measurements on the diagram. 3.3 times 42 divided by 4.3, and I'm getting 32.2. So I'm getting R as 32.2. Because I was on a computer, it may not be very accurate. So, but you can verify 32.2 meters per second. Let's verify with the calculation, the value will be very close. When you are drawing on your book and you're very accurate in measurement, you measure accurately, you'll get a more precise value, a more accurate value. So instead of using the scale, I'll use the cosine rule. To use the cosine rule, I must know the angle between the two vectors after joining them head to tail. And this angle is 54 degrees without even any problem. Okay, so if that is 52 degrees, so using the cosine rule, V of the resultant is going to be the square root of 42 squared plus 23 squared minus 2 times 42 times 23 cos of 54. So I just press my calculator. 42 squared plus 23 squared minus 2 times 42 times 23 cos of 54. So that is 1. Then I find the square root of the answer, which is 34. So the most appropriate value is going to be 34.0 meters per second. That's method of the cosine rule. Then I can use resolving. Let me try out resolving. I'll use resolving here. This is now method 3. I will resolve the velocity of the wind is having two components. In the horizontal, it points to the right, and in the vertical, it points downwards. So the velocity in the vertical is going to be 42 upwards minus 23 cos 54. This will be downwards. 23 cos 54 is downwards. I've resolved this downwards. I mean, in the vertical, it points downwards, and in the horizontal, it points to the right. And in the horizontal, to be 23 sine of 54. So V in the X is 23 sine of 54. So we now find the resultant velocity by Pythagoras theorem. So that will be the square root of 23 sine 54 squared plus 42 minus 23 cos 54. And this is also squared. So let's verify with a calculator. So open the brackets, 23 sine 54, and that is squared, plus open another bracket, 42 minus 23 cos 54, and that is squared. That gives us that answer, and we find the square root. Yes. Okay, let me repeat it again. I'll repeat it with the most complex one, which is 42 minus 23 cos 54. Then I square it. Then I add this to 23 sine 54, and this is squared. No, this one is squaring the angle alone. Sorry. 42 minus 23 cos 54. Then we square this, plus I'll open one bracket and one bracket, 23 sine 54 4, close that bracket, and close the outer bracket and square. Yes, then find the square root of the answer, which is 34. So V resultant is still 34. So you use any method in case they don't specify, but many times they specify scale or resolving. They rarely tell students, they have never told students to use the cosine rule. But if they have not told you which method to use, you can even use the cosine rule. Okay. But see, the engine of the aircraft in B stops. The aircraft then glides towards the ground with a constant velocity. Constant velocity, no resultant force. At an angle theta to the horizontal as illustrated here. The aircraft has a weight of 56 newtons and travels a distance of 280 meters from X to Y. The change in gravitational potential energy of the aircraft from X to Y is 6,100 joules. Assume there is now no wind. Calculate angle theta. So to calculate angle theta, we shall need the vertical height. We shall need the vertical height h, because sine theta is equal to the opposite, which is h, over the hypotenuse, which is 280. But from the change in gravitational potential energy, which is equal to mg times the change in the height, we can find h. So it means the height h is equal to 6100, that is the change in gravitational potential energy, divided by mg, which is the weight. Mg is the weight, which is going to be 46. So it means sine theta is going to be h, which is 6100, divided by 46 times 280. So what is theta? Theta is the sine inverse of that. So 6100 divided by 46 times 280. Then the sine inverse, also shift the sine inverse of the answer, which is 28. So theta is 28. It is 28.3, or approximately 28 degrees. Then calculate the magnitude of the force acting on the aircraft due to air resistance. So the change in potential energy must be for the work done against air resistance, since the speed is constant. So the change in potential energy is equal to the work done against air resistance since there is no change in kinetic energy. How do we see that there is no change in kinetic energy? V was constant. V is constant. The speed was constant. Therefore, the work done is going to be, and by the way, remember, work done is equal to the force times the distance. So the work done is going to be 6100, and the force is what we want to find. Then the distance is 280 from X to Y. So F is 6100 divided by 280. 6100 divided by 280. That gives us 21.79, or 22. So that would be 22. The aircraft in C travels from X to Y in a time of 14 seconds. The figure shows that as the aircraft travels from X to Y, it moves directly towards an observer who is standing on the ground. The aircraft emits sound as it travels from X to Y. The observer hears sound of frequency 450. Remember, it is moving towards. The speed of sound is 340. Capture the frequency of the sound that is emitted by the aircraft. So let's first of all find the speed of the source from X to Y. The distance is 240 and it takes a time of 14 seconds. Time is 14 seconds. So it means the speed here is going to be 280 divided by 14. So the speed of the source is going to be 280 divided by 14, which I think that is 20 meters per second. So the aircraft is moving at that speed between X and Y. And then if it takes 14 seconds, since it is moving towards the observer from waves, the observed frequency is going to be V over V. Here it will be minus the speed of the source times frequency of the source. It will be minus because it is higher frequency since it is moving towards. If it was moving away, it would be plus because away would be lower frequency. So 450 is equal to 340 divided by 340 minus Vs, which is 20. Then we multiply by Fs. So here I will just press my calculator. I'll simply say 450 times, open brackets, 340 minus 20 divided by 340. So that is 423. So the frequency of the source is 423 Hertz, approximately 420. Okay. Water leaves the end of a hose pipe at point P with a horizontal velocity 6.6 meters per second as shown in the figure. Point P is a height h above the ground. The water hits the ground at point Q. The horizontal distance from P to Q is 3.5. Air resistance is negligible. So equations of motion can apply because the acceleration is constant. Assume that the water between P and Q consists of non-interacting droplets of water and that the only force acting on each droplet is its weight. Explain briefly why the horizontal component of the velocity of the droplet of water remains constant. So we have been seeing velocity remains constant in the horizontal because the acceleration is zero, and the acceleration is zero because there is no force in the horizontal. So we simply say that the force on the droplet of water in the horizontal direction is zero. The force on the droplet of water in the horizontal direction is zero, so the acceleration is zero. So acceleration is zero. There is no acceleration in the horizontal. Show that the time taken for the droplet of water to move from P to Q is 0.53 seconds. I think that is easy. P to Q, we can consider horizontal motion since they gave us the horizontal distance. So S in the horizontal should be equal to the initial velocity in the horizontal times T plus a half acceleration in the horizontal times T squared. Remember, in the horizontal, we have just said acceleration in the horizontal is zero. So this part becomes zero. S in the horizontal is 3.5 equals to the initial velocity in the horizontal is 6.6, then times the time t. So t is 3.5 divided by 6.6. 3.5 divided by 6.6, that is 0.53. So this is 0.53. calculate the height h. We shall consider vertical motion, use the same formula s in the vertical, initial velocity in the vertical times t plus a half acceleration in the vertical, which is acceleration due to gravity, times t squared. Note that initial velocity in the vertical when the body is projected horizontally is 0. Therefore, s in the vertical is h, this part will be 0. So we have a half times 9.81. The time is the same, so that will be 0.53, and this is squared. So 0.5 times 9.81 times 0.53, and that is squared, which gives us 1.3778, or 1.38, which is approximately 1.4. So this will be 1.4. For the movement of the droplet of water from P to Q, state and explain whether the displacement of the droplet is less than, more than, or the same as the distance along its path. Of course not. Displacement is the straight line distance, that is from P. To find the displacement, I need the straight line distance from P to Q. And you see that the straight line distance is less than the distance PQ. Therefore, the displacement is the straight line distance from P to Q. Displacement is the straight line distance from P to Q. So it is less than the distance along the path. It is less than the distance along the path. Or you can just simply say that displacement is the shortest distance from P to Q, so it is less. Or you can simply say displacement is the shortest distance from P to Q. Okay, calculate the magnitude of the displacement of the droplet of water that moves from P to Q. So displacement, we have S in the X, we have S in the Y, so we just find the resultant by Pythagoras theorem. The displacement in the vertical is 1.4. That is the vertical height. And the displacement in the horizontal, the distance in the horizontal is 3.5 meters. So we need the resultant. So the resultant displacement is going to be the square root of 1.4 squared plus 3.5 squared. 1.4 squared plus 3.5 squared, then square root of the answer, which is 3.8. Define velocity. Of course, velocity is the rate of change of displacement. So velocity is the rate of change of displacement. Rate of change of displacement, that is the velocity. A rock of mass 7.5 kilograms is projected vertically upwards from the surface of the planet. The rock leaves the surface with a speed of 4 meters per second, so it is leaving with 4. So here it has reached the maximum point, maximum height. I think this is 2.5. The variation with velocity, with time of the velocity is shown there. So we see it reaches maximum height at 2.5 because at maximum height, velocity in the vertical is 0. Assume that the planet does not have an atmosphere, meaning air resistance can be ignored, that the viscous force acting on the rock is always 0. Determine the height of the rock above the surface of the planet at t equals to 4 seconds. So here it has gone up, here it is coming downwards, and it reaches the meter hill. Okay, so it is actually at a certain height, it lands at a certain height. The rock leaves the surface of the planet with a speed of 4 meters per second at t equals to 0. So distance is going to be the area under the graph. We are just going to get the difference because we want height above of the rock above the surface of the planet. It goes to maximum height and it comes back. So this is the planet. It goes to maximum height and comes back. But we see that the area here is smaller than the area there. So it means it does not reach the planet. So it stops somewhere there. So we want the maximum height, the height h above the surface of the planet. So we shall get the area when it is going upwards minus the area when it is coming downwards. So displacement is equal to the area under the graph. So this will be, we are going to get the area when it is going up, which is a triangle, a half times the base, which is 2.5, times the height, which is 4. That is when it is going up. That is distance when it is going up, minus distance when it is coming down, which is also a half. The base is 4 minus 2.5, which is 1.5. Then times the height is, I think this is what? It stops here. And I think this is 2.4, negative 2.4. So this is, the height is going to be 2.4. So we just subtract. So 0.5 times 2.5 times 4 minus 0.5 times 1.5 times 2.4. So that is 3.2. So the height is 3.2. Then determine the change in momentum of the rock from time t equals to 0 to time t equals to 4. So momentum is mass times velocity. We want the change. So change in momentum is going to be the mass, which is 7.5 kilograms, times change in velocity, which is, say, 4 minus negative 2.4, or the other way around, negative 2.4 minus 4, which gives us 7.5 times 6.4. That is 48. So the change in momentum is 48. Whether it is negative or positive, the magnitude is the same. Determine the weight of the rock. Because they say there is no air resistance, the only force acting is the weight. So the weight of the rock is going to be the force that we have just obtained, because the force is equal to the rate of change of momentum. So this is going to be equal to the change in momentum, which is 48, divided by the time for which the momentum changed was 4.0. So that means, I think 48 divided by 4 is 12. So the weight is 12. Alternatively, we can first find the acceleration due to gravity by getting the mass times the change in velocity over time. I mean, you get g by getting the change in velocity over time, then you multiply by the mass. It is the same thing here. In practice, the planet in B does have an atmosphere that causes a viscous force to act on the moving rock. State and explain the variation, if any, in the resultant force acting on the rock as it moves vertically upwards. So let's think of this. The rock is having a weight downwards. This arrow here is showing the direction of the motion. Motion is not a force, by the way. I'm just showing direction of motion. It is upwards. If it moves upwards, it means there is a viscous drag, which is Fv downwards. So state and explain the variation, if any, in the resultant force acting on the rock. So the resultant force increases. Actually, it does not increase, it actually decreases because the viscous force decreases. Since for upward motion, the velocity decreases. The velocity decreases, it means that the viscous drag decreases. So if the viscous drag decreases and the weight is constant, it means the resultant force also decreases. Therefore, we can simply say that for upward motion, but if it was falling downwards, the viscous force upwards would be increasing because moving downwards, the speed increases. So the viscous, for upward motion, the velocity decreases. Velocity decreases, so viscous force decreases. Viscous force decreases. Since the weight is constant, it means the resultant force decreases. So if it is moving upwards, the velocity decreases when it goes against gravity. So that means, and remember, viscous force depends on the speed. Viscous force is directly proportional to speed. Moving against gravity, speed must decrease, meaning viscous force decreases. And remember, the resultant force is the sum of the weight plus the viscous force. So it means the resultant force decreases. If it was falling downwards, then it would mean, for downward motion, it would mean that actually the speed is increasing when it is falling, which would imply that the viscous force increases, and still, if it is falling downwards, the weight is downwards, the viscous force is upwards, so the motion is downwards because the viscous force is upwards. Still, as it falls downwards, the velocity upwards increases, the viscous force upwards increases. So still the resultant force again decreases also because the resultant force is now the difference between the two. It still decreases. Okay. A man standing on a wall throws a small ball vertically upwards with a velocity 5 meters per second. The ball leaves his hand when it is at height of 3.1 meters above the ground as shown. Assume that air resistance is negligible. Show that the ball reaches a maximum height above the ground of 4.7 meters. So let's first of all find the height it goes from his hand. So using v squared equals to u squared plus 2as. We are finding the height it reaches, the height it goes from his hand, that is the height h. It goes from his hand. So v squared at maximum height v is 0, so 0 squared is equal to initial velocity is 5.6 squared minus 2 times 9.81, then times the height h. So the small height h above this hand is going to be 5.6 squared divided by 2 times 9.81. So this is going to be 5.6 squared divided by 2 times 9.81. So that is this is 1 point. Okay, I will not simplify that. So the maximum height the maximum height h would be equal to h plus 3.1. So this would be 5.6 squared over 2 times 9.81 plus 3.1. So this will be, I'll just add it on that answer, 3.1, which gives me 4.6983. So this is 4.698, which is approximately 4.7 meters. 4.698, approximately 4.7 meters. So that is the maximum height above the ground. Then the man does not catch the ball as it falls, meaning it goes and comes back to the ground. Calculate the time taken for the ball to fall from its maximum height to the ground. So we shall simply use for maximum height, or we can use when it is falling from the maximum height. Calculate the time taken for the ball to fall from its maximum height to the ground. So we are going to consider it when it is leaving maximum height, where u is 0 initially. So from maximum height, it means it starts with the 0 when it is falling. So u is going to be 0, and I will use s is equal to ut plus a half at squared. So s in the from maximum height, it is going to fall through a height of 4.7, which we have seen above. This part will be 0 plus. So here we cannot say minus because we consider it when it is just falling from rest at the maximum height. A half times 9.81 times t squared. So t is going to be 2 times 4.7 divided by 9.81 under the square root. 2 times 4.7 divided by 9.81 of the answer, that is 0.98. 0.98 seconds. The ball leaves the man's hand at time t equals to 0 and hits the ground at time t equals to t. On the figure, sketch a graph to show the variation of the velocity v of the ball with the time t from t equals to 0 to t equals to t. Numerical values of v and t are not required. So since it goes up the maximum point, means initial velocity, it starts with a certain velocity, then it goes to maximum height. That means the velocity becomes 0 at maximum height. So let's say the velocity becomes 0 after certain time t. Then it reaches the ground after some time capital T. So I'm going to draw a graph which crosses x-axis. But this, since it falls below the point of projection, it means its velocity continues increasing until it reaches the ground. So it means it hits the ground with a higher velocity than the one it started with when it is going upwards. So I'll draw a line which stops at a higher value of velocity at t, at capital T. So that could be my graph. I think we have done a similar question before. Okay, so that will be the graph. That will be our graph. State what is represented by the gradient of the graph in C. Of course, the gradient is the acceleration of the ball. Gradient is acceleration. Area under the graph is displacement. The man now throws the second ball same velocity and from the same height as the first ball. The mass of the second ball is greater than that of the first ball. Assume that air resistance is still negligible for the first and second balls. Compare the magnitude of the acceleration. This one is the same. The magnitude is the same because it is not dependent on the mass. Not dependent on the mass. then the speeds with which they hit the ground. Since the speed is also not dependent on the mass, because we are using equations such as v squared is equal to u squared plus 2as, this one has not changed, so the speed is the same. So the speed is going to be same speeds. It is not dependent on the mass. Okay, I think this is the last question. This could be the last question. Everything comes to an end, just like high school is coming to an end on your side. Define velocity. Velocity is the rate of change of displacement. A constant driving force of 2,400 newtons acts on a car of mass 1,200 kilograms. The car accelerates from rest. Initial velocity is 0 in a straight line along a horizontal road. Assume that the resistive forces acting on the car are negligible. Calculate the acceleration. So the acceleration is constant, so the resultant force F is equal to mass times acceleration. So the acceleration is equal to the force, which is 2,400 divided by the mass, which is 1,200. So that means we have 2,400 divided by 1,200, and that is 2. So that is 2.0. On the figure 3.1, sketch a graph showing the variation with time t of the velocity v of the car for the first 20 seconds of its motion. First 20 seconds of its motion, label this line A. First 20 seconds of its motion, the acceleration is 2. So the acceleration is 2. It starts from rest, so v equals to u plus at. So let's see, the velocity is going to be u. It starts from rest, that is 0, plus acceleration is 2 times 20. So final velocity is going to be 40. So at 20 seconds, velocity is 20 meters per second. So I just look for that to be a straight line. When t is 0, v is 0. When t is 20 seconds, v is 40. I think this is 40. I'll put there a ruler to see that it is 40. Yes, it is 40. So I'll increase the thickness and I draw a thicker line which is visible. So this line goes through the origin. I missed the point. Okay, so they said label this line A, so I'll label this line A. In reality, a resistive force due to air resistance acts on the car in B. The resistive force increases with the speed. It becomes equal to in magnitude to the driving force at t equals to 12 seconds. That means here terminal velocity is reached at 12 seconds. So the line must be horizontal at 12 seconds. On the figure, sketch a second line to show the variation with the time t of the velocity v of the car for the first 20 seconds for its motion. Label this line B. So since it reaches terminal velocity at 20 seconds and there is air resistance, the new graph is always going to be below the first graph. It is always going to be below the first graph, but it becomes horizontal at 12 seconds because this is when the driving force equals to, this is when the resistive force increases with the speed until it becomes equal in magnitude to the driving force. When the resistive force equals to the driving force, resultant force is 0, acceleration is going to be 0. We have reached terminal velocity. Therefore, we just ensure that the line becomes horizontal at around 12 seconds. At around 12 seconds, the line becomes horizontal. So I'll just consider that part there. So I'll draw a curve which becomes horizontal at around 12 seconds. I have to make this horizontal starting at 12. Of course, after 12, it will be a horizontal line. So let me begin by drawing a horizontal line here. Then now, so I can start from here. It is not easy, but I'm going to try. I don't want it to look like it is a horizontal line. So I'm going to be forced to make it bigger. Okay, something like that. Okay, so something like that. It becomes horizontal at 12 seconds because at that point it will have reached terminal velocity. Okay, describe how the velocity of the car at time t equals 20, the driving force is increased to 300 newtons. This and remains constant at this value. Describe how the velocity of the car changes due to the increase in the driving force. Remember, initially the driving force was 2,400, but they are saying at 20 seconds the driving force is increased to 3,000 newtons. Even when there is resistance, there is a resistive force. So what happens when the driving force is increased to 3,000 newtons so that it is now greater than the resistive force? So because the driving force is now greater, it means the car will now have an acceleration. It will actually accelerate to a new value. But remember again, air resistance increases with the speed. So it will accelerate to a new value of velocity. And then a point is still going to reach when the air resistance is equal to the driving force. Again, we shall reach terminal velocity. By this time, the terminal velocity reached here will be higher than the one we have reached before, when the driving force was 2,400. So we say the car will have an acceleration to a new value, or to a new and higher value, to a new and higher value. To a new and higher value of terminal velocity, Because now the driving force is greater, it means the car will be forced to accelerate to a new value, a new higher value of terminal velocity, or the velocity will increase, or you can simply say the velocity will increase to a new terminal velocity. The velocity will increase to a new terminal velocity, because now it will require more air resistance to balance with the driving force of 3,000. That means the car will have accelerated to a higher velocity, which will be which means to have access to a new terminal velocity that is higher than the one we had before. I think that is the end of kinematics. Just in case of any errors, I will be sorry for that. I know I'm human. I'm bound to make some errors because of several conditions surrounding me. For that reason, I hope you have learned something from this, and I hope you have enjoyed this video. I wish you success in your exams. Please make sure you are spending much of the time studying and going through the past paper questions. You will make it. See you in electricity. The next unit will be electricity, and that will be the last unit, electricity. Bye bye.